So we'll start in a minute, and we'll go over blockchain and privacy. Just quick question, how many people here are familiar with blockchain technologies? Like how they work? Sort of, a little bit? Okay. Okay, cool. How many people here are, oh wow, there's a bunch of people all of a sudden. How many people here are familiar with ring signatures or zero knowledge proofs? Does that come up in any prior coursework? Okay, so we're not going to go to them in detail because that's like a whole class by itself, but we'll kind of give the intuitions. And how many people here, just so I know, how many, did people all over the place on this, how many people here have heard of or know about what's called consensus algorithms? Okay, so this will be new. Okay, cool. Just want to try to see where people are. So we'll start now since everyone's here. So I'm Harry Halpin, and I run a blockchain startup that employs some KU Leuven people called NIM, and we're a blockchain privacy startup. I'm going to mention us, but we're not the main focus. The main focus is a general analysis of blockchain and privacy. So a lot of these are the same slides we used to use. Oops, let me go over here. There we go. At MIT, so I didn't create all these slides myself. These slides are due to Gary Gensler, currently head of SEC, Naya Narula, Madars Versa, and although some of the slides are me. So we're going to try to get kind of first a big picture of what is a blockchain system, what makes it different than other systems. So the way you want to think about blockchain systems is not just a blockchain, though it's a pretty good way to do it, but you have a system, any kind of system, social parts, technical parts, where the current and past state of the system is secured by cryptography, and the future of the system is determined by economic incentives, right? So you have some economic process, assuming that people want to, for example, make more money or get more votes or get more reward. That should make the system's behavior stable and predictable in the future. And the system's past behavior, which determines its future behavior, is secured by some form of cryptography. There's many, many different options out there. We're going to mostly talk about Bitcoin, and then we're going to talk about Bitcoin's privacy problems. We'll probably mention Ethereum, but not go too deeply into it, and mostly focus on, oops, sorry, let me close that down, and mostly focus on Monero and Zcash, which are kind of the privacy alternatives to Bitcoin, because Bitcoin has very poor privacy. So if you're interested in cryptoeconomic systems, there's a lot of surveys. There's a particularly good one at a new MIT journal called Cryptoeconomic Systems. But let me just explain, like there's a huge space here, right? So you have the original system, which was called Chaumian eCash, which actually produced by a professor affiliated with KU Leuven and at Amsterdam CWI called David Chaum. So you hear it called Chaumian eCash. He's very well known for inventing mixed networks and generally doing very creative cryptography. His company was called DigiCash. That was probably the main focus of cryptoeconomic systems for like 20, 30 years. So we'll discuss how some of those design decisions played out, and it had privacy, which is very nice. Then you have Bitcoin, which was the kind of successor to Chaumian eCash. Extensions of Bitcoin linked to Ethereum, what's also called altcoins or alternative coins, which are various kind of variants on Bitcoin or Ethereum. Then now you have a big rise of centrally banked digital currencies. So these are when the state itself, we're not going to talk about these too much, where the state itself runs a blockchain. So even if you're like skeptical about blockchain systems, you have to realize that most banking systems are going to be running on blockchain. So for example, in Europe, a wholesale blockchain-based system, so wholesale is not the consumer, but like the banks themselves already are using blockchain technology to communicate and do settlements. That's I think been launched. China already has a CBDC. I know a little bit less about it. The USA is debating it, but there has been, at least in the USA, some attempts in the state of Massachusetts with MIT to do privacy-enhanced centrally banked digital currencies. Because obviously one of the dangers you would have of all your currency being digital is that it's a large surveillance mechanism. So every purchase you know is kind of recorded by the state. Now, of course, with Bitcoin, every purchase you know is public. So it's kind of like Twitter for your bank account. So every time you say you buy something, everyone on the planet knows. We'll discuss why that is shortly. And it's actually for pretty good reasons. So again, just to go a bit more detail, crypto economic systems have a blockchain. Blockchains are not magic. They're just, all they do is they use cryptographic hash functions, usually in combination with digital signatures, to secure the past state of the system. And every user is identified with a cryptographic key. So do we all know what hash functions digital signatures are? We've encountered them at some point? Okay, so cool, I don't have to explain that. The incentives reward honest actors in the system to create a predictable, but not necessarily 100% predictable, future state of the system within the flexibility of the real world. So the reason why sometimes you want to use incentives rather than like a purely like deterministic future state of system is because you don't know who's going to be using the system, how much money is being going through it, what it's going to be used for. So this gives you, using incentives gives you kind of some level of flexibility. And then we use consensus algorithms. And so the reason you use what's called a consensus algorithm, we'll discuss them in a bit more detail, but it's a technique from a field of computer science called distributed computing. So this is where you have many different computers working together to accomplish a single goal. So if you use G Drive, it appears you're just talking to Google, but actually there's many different servers with many different people's data, and they run a consensus algorithm behind to make sure that your data is replicated and backed up so you don't delete it, and all the servers have the same copy of your data. So that's one way to think about distributed computing. And a consensus, like how do you make a consensus? For example, you might vote, right? We might say, well, you probably don't want to do this with money, but you would say like, you know, do we all have copies of the same file? And then one person has a file which is different, but 90% of the people have a file which looks the same, then that file that looks the same is the correct version of the file. So that's a very quick example of a consensus algorithm. And the reason you use a consensus algorithm is because you cannot, unlike in centrally ran systems and decentralized systems, there might be adversarial users. So you got to assume that some parts of the system could either have faults, just mechanical faults, the server goes down, there's some problem, you don't know what, or they could be actively malicious, trying to steal your money, change the consensus. So inside Google, you assume Google is running all the servers. You don't have to worry too much about adversarial use cases, but you still have faults, right? So this is why Google uses a lot of consensus algorithms internally. And blockchains also use consensus algorithms because there may be adversarial users trying to take advantage of the system and break it. And so if you want, it's a bit old, but to be honest, it's been updated fairly recently. It's a good textbook. If you're really interested in the subject, the best textbook out there is Bitcoin and Cryptocurrency Technologies, a comprehensive introduction, and has a set of slides and video online, which we are not using. So what is the problem that Bitcoin was published by this anonymous guy called Satoshi Nakamoto, who we still don't know? What is the problem that Nakamoto is trying to solve? So this is the kind of the properties a system should have. Any blockchain system, including private ones, but public ones as well. So you should have what's called no stealing, right? So this is particularly what you need for a money-based system. Only the person with the money can move their money. So how do you know if someone wants to move their money? Well, they have to sign the transaction. They sign it with a digital signature. No double spending. If I move money to you, I can't move the money to someone else. I move money, it's removed from my balance, I can't move it twice. So that requires a global ledger. And third is, where does the money come from? Right? So traditionally, a bank just kind of makes it up. They say, you know, maybe they talk to the government and they're trying to balance some inflation. So in the United States, you have the Federal Reserve System. In Europe, most countries have their own central bank. I assume Belgium does. I actually don't know. But they kind of print the money. And then the question is, like, when I'm the Federal Reserve in the US or the Belgian Central Bank and I print the money, what you usually do is you give the money to the large banks in the country. So there's the kind of immediately give it to the banks, and they put that money in circulation. So for example, during COVID, there was like a crisis, at least in the United States. People said, okay, everyone gets a bit of free money to keep the economy going because people were worried the economy was going to crash. So the Federal Reserve just made up a bunch of money and handed it to the banks that then distributed checks to all the people. So that was just new money created in the system. And one of the dangers of putting new money in the system is it could lead to inflation, right? But inflation could also be a good thing, right? So if your economy is growing, you have a growing economy, you need some inflation in the system because otherwise, there's not enough money to spend, basically. So inflation within bounds is generally considered a good thing by most mainstream economists, although Bitcoin people a little bit disagree often. But there is this general problem of what's called fair money creation. And Bitcoin and blockchain technologies, they have different solutions for this, but we're going to go over the original one because it has some interesting privacy properties called proof of work. Have people heard of proof of stake here? Anyone? Okay, so you've heard of it. So proof of stake is, we'll mention it. And the big hard issue is, can it be decentralized? So, okay, so we're not going to go over this because you all know what digital signatures are, but basically, if you ever use cryptocurrency, it's just QR codes, and those QR codes are just digital signatures. You send and receive money by basically scanning a QR code, which is a public key. And you can send money because you have a private key on your phone or device, and that private key can then make a digital signature and prove that you sent the money to the public key. So now Bitcoin address is not the raw public key, because those can be quite big. So what Bitcoin addresses are is, well, of course, when you create your cryptocurrency account, you create a private key. So if you go install a wallet, they say, hey, what's your private key? You click a button, and maybe you generate some randomness by moving your mouse around. And then you get a bunch of words, usually. That's your backup. That's actually, that's your key. That's your private key. Then you just do a little bit of elliptic curve multiplication, right? So you take an elliptic curve group, multiply the private key, and then you get a public key. And then what Bitcoin does is kind of wacky thing, which is not entirely necessary. Because the public key is so big, you basically run it through a public hash function, which for some reason they use they chose kind of randomly, but SHA-256, good. RIPE-MD 160, not really clear why they threw that in there. But then you encode it, and that's your Bitcoin address, right? So for some reason, Bitcoin, because I guess they weren't sure if SHA-256 was secure, which to our knowledge it is, they run it through two hash functions. They also run it through I think, insecure hash function called RIPE-MD 160, or at least less well studied. And then how blockchain works, yeah. I just explained. So it's because I think the designer of Bitcoin was not a cryptographer. So he was like, oh, what if one is broken? So we'll use two. I agree it doesn't make sense, but that's just what he did. So as a non-cryptographer, it makes some sense. You're like, oh, we'll have a backup hash function now. Obviously, because you assume, okay, maybe there's a bunch of collisions on a RIPE-MD, but there's not on SHA-256 or vice versa. I think that's what no one really knows. He didn't explain, just saying it's what he did. It's not necessary from any. So most newer blockchains typically just use one. So, because it's a better design, but it's fine. Hashes are cheap, and you're just using the generate public keys, so not a big deal. And then how a blockchain works is you have these things called blocks. These blocks have a lot of stuff going on in them. You typically have actually a bunch of metadata, and you have the block itself, which you hash, and then and each block is signed, and then typically for each transaction, because you want to have a lot of transactions in a single block, you put in what's called a Merkle tree. Do people know what Merkle trees are? So Merkle trees are just kind of hash functions that you arrange in a certain way. And then the whole point of this, again, just to go back to why we're doing this, is that because each block hashes into the next block, it's a chain of hashes, maybe a better way to think about it than a blockchain, so that if anything is altered, you can detect it, right? So every single transaction in the past is put in a Merkle tree. These are all put in blocks. You get the hash of the block. The hash of new blocks is dependent on the hash of previous blocks. So any attempts to alter a single transaction are detectable by the whole chain. Right? So that's why you have a blockchain. So no transaction can be altered. It's actually not probabilistic, really, unless you consider hash functions probabilistic. So any change should be detectable because it will destroy the integrity of the chain. So that check on the integrity of the chain, so you're saying, is this the right chain? You check the hash function, and you should be able to go into it and check. And if you took every single transaction, check the signature, hash them, hash them, hash them, you can build all the transactions into a single big hash. You can check that, and that's the checking the integrity of the whole chain. Usually, when you use a Bitcoin or other cryptocurrency wallet, you do not download the entire history of all transactions into your wallet. You just check the hash. Now, other people do maintain, and we'll talk about that later. But the problem is, again, we're assuming an adversarial system. What if there's a conflict? So have you guys studied the Byzantine general problem anywhere? Okay, so you know it, great, so I don't have to cover it. But basically the issue is, typically the problem in classical computer science is I have a bunch of people, they need to coordinate an action, like who's going to attack, I guess, Constantinople or Istanbul, depending on how you feel about that. And when do you attack, when do you retreat, how do you pass those messages and make consensus? And so the classic paper on this, which is actually worth reading, it's really readable, is the Byzantine generals problem. But there's a big difference, right, between the Byzantine general problem and the problem that Bitcoin is trying to solve. So if you ever look at Bitcoin, the first thing you would think is, why don't they just use a classic consensus protocol? Like typically you would say like the Nancy Lynch's PBFT, it's pretty well known, been studied for 30 years, everyone knows about it. It's not like there's not solutions to this problem in the literature that are fast and efficient and have good security bounds, like 1/3 of the people are corrupt or something. But Bitcoin is different and blockchain is different because they're what's called permissionless. So what permissionless means is that at any point, anyone can join the consensus system, right? So that's very different. So usually, historically in computer science, you say, that, oh, there's only so many servers that need to have consensus. So we want to deal with an unknown number of participants, right? So that's kind of what changes the game. And this actually is maybe the big breakthrough of Bitcoin. So just to review consensus algorithms, which I won't really review very quickly since you guys know about it, but like let's say we want to design a consensus system where we know there's only going to be so many people involved, which typically in blockchain space is called validators. So what you would typically, the simplest consensus algorithm, and this will explain proof of stake really quickly, is you have a leader, and that leader is one of your validators or participants in the consensus algorithm, and they are producing blocks. Remember, they're saying, okay, these are the right transactions. They check it and they make sure the hash is all kind of verified and everything adds up. Now, the danger with this is, what if you have a bad validator? So you gotta, everyone has to check them to make sure they're not lying about does the integrity check of the hashes pass and the balances add up. But you can imagine a really simple and very fast consensus algorithm where you just choose a leader randomly, right? And if you choose that leader randomly, and let's say they produce blocks for some amount of time, maybe let's say 40 blocks, and you say, okay, cool, then you have some shared randomness, and you choose another leader randomly, right? So you do a little voting procedure, and if anyone is offline, they get elected to be leader, or they don't vote, or they don't check, they get what's called slashed. So what does slashing mean? Well, and what we say is, well, we have to vote, and we have to choose who's the leader. Now, how do you choose who's the leader? Well, maybe it's, one person, one vote, one validator, one vote. That's one way to do it. But realistically, maybe certain computers are more trusted than other computers. So they have a higher probability of being chosen. How do you determine that probability? One way of determining that probability is how much money is on that computer, right? So if I have $1 million and I put it on a computer to run a validator, it would be chosen let's say with 10x the probability of someone that only put $100,000 on that computer. That amount you put on the computer, that $1 million, or that 100,000 or whatever it is called your stake. So and so your probability of being chosen to be leader is then dependent on your stake. Right? Now and then if your computer doesn't vote honestly, doesn't check honestly, is elected leader and doesn't produce the blocks, you get what's called slashed. And that means the money that you put on that computer, the stake, gets removed. Maybe not all of it, probably some percentage, but generally you lose money. So the theory is everyone has some money on their computer, that's cool, and you lose money if you don't participate in the consensus algorithm properly. But the problem with that system, and this is the system used by blockchains such as Ethereum, is that effectively in order to join the set, you have to put money on your machine, and it's not really permissionless. You can't come in and out anytime. There's kind of a set number of rounds, and so it's not ideal. So what Satoshi Nakamoto did is he invented a new consensus system, which we'll explain, called Nakamoto consensus. And the short version is you have people producing blocks. I'm producing a bunch of blocks, you're producing a bunch of blocks, I'm checking it, other people check it. We'll go into this in a little bit more detail. And the person with the longest chain wins. So what does that mean? That means we use proof of work. So this is from the Bitcoin white paper. So what does proof of work mean? So there was originally, you guys went over mixed nets, I think, last time with Leonard. So what's one of the problems with mixed nets? Mixed nets were invented for email, right? So I want to send email to you anonymously. Right? So what's a problem that could happen if I'm running a machine that's sending anonymous email? Any thoughts? Like, let's say, if I'm running that machine, what's something that people could do with my machine that I might not want them to do? Okay. Yeah, they could send spam. So you've just created a perfect spam machine, and that is indeed what happened with early mixed nets for email, such as Mixmaster and Mixminion. So what happened is that this guy called Adam Back, who many people think is Nakamoto, invented something called Hashcash. So what Hashcash says, it was the first proof of work system. It was based on a crypto paper by, I'm forgetting, I think Dworkin and Naor. But effectively it said, well, we want to charge some tax because the reason people send spam is it's free. But if I charge you like 5 cents, then you're not going to spend it, you're not going to send the spam. Now, the other thing you could do is just list, like, here's the people that are bad that send spam, and here's people that are good, but this requires identifying all your users, which kind of is like against the point of making an anonymous communication system. So it's easier just to charge people, and the question is, how can you charge people anonymously? And we didn't really have working anonymous cash then. So he said, well, we'll just make them run a hash function a bunch. We'll describe that in a little bit more detail later, but the theory is that if I run a hash function, produces a random number, if I have to prove that I've generated a bunch of random numbers, then I'm going to spend a few cents or a few dollars in computing time, and that's like a tax on sending those anonymous messages out, right? Now, the inventor, one thing we know about the inventor of Bitcoin, we don't know who he is or she is, but we do know that they knew about mixnets and that they probably ran a mixnet email server. And the reason is this quite obscure technique called Hashcash to prevent spam in mixnets was used to do something that it was not intended to do, which is to run a consensus algorithm. Right? So the whole point of proof of work is that essentially, so I can use proof of work to basically show that I've done some certain number of hashes and that therefore I can send this email. I can also do proof of work to prove that I've done an amount of work while without revealing my identity, like in the traditional consensus algorithm, and join a consensus algorithm. So let's just talk a little bit more about proof of work because it's confusing a little bit, and it's good to understand how it actually works. So we'll talk about mixnets first, then we'll talk about blockchain. So this is pretty, so you take the email, maybe just the header of the email, you put it through a hash function, and you get a random number out. That's just how hash functions work, right? And then how do you show that someone's done so many hash functions? Well, you have what's called a difficulty, sometimes called a target, and that target basically says that the result has to have a number of leading zeros, right? So maybe if I have to keep hashing, I keep throwing that email through the hash function with a nonce, a random number, right? So you just not, because otherwise it's not deterministic, right? You throw a random number in, throw an email in, and then you get a result. And if that result has a 0 in front, I've proved I've done a certain number of hash functions. Not really deterministically proven, but I kind of probabilistically proved it. It's unlikely that I would be able to just magically, I mean, you can magically hit that leading 0 on the first try. It's going to take you a few tries to try. And then the thing is, because hash functions, right, their kind of range or their output is random, right? That's the whole point of a hash function. It's like a random oracle that you might have. You can say, well, what's harder than producing 1 0? How about producing 2 zeros? Right? That would be harder because I have to run even more. The chances that I actually just put a hash function and a random number together is pretty hard, right? So they get 2 zeros and the result is harder than 1 0. And then 3 zeros and the result, we don't care about the rest, is harder than 1 or 2. And this is quite interesting because the cool thing is, if I have the original email and I have the random number, and this is a public hash function, I can then prove to you that I have the right random number. And it's very hard to predict, it's impossible, at least if the hash function works, to predict what that random number should be. Right? So it's a pretty cool system, quite inventive. And then the question is, can we use this for blockchains? And this is how it works. So what I will do is the whole point is I would like to join this consensus algorithm. And why would I want to do that? If I join people generally don't join consensus algorithms for fun unless their boss tells them to. So this is a permissionless system. There's no boss. We don't know who's even in the consensus algorithm. This is pretty unusual from a computer science standpoint. So what we do is we say we pay them, that if you can successfully join this consensus algorithm, you basically get paid. And that payment is called a coin-based transaction, by the way. So that's what solves the who prints the money, the fair minting problem or the inflation problem. And then what happens is the exact same thing happens to Bitcoin as what happens with email over like a mixnet with proof of work. Let's just run through the example. I have a Merkle tree, which is connected via a hash to the previous Merkle tree and all the Merkle trees. And this is my block. And then in order to add a new block, I have to get a certain number of zeros into, I take the hash of the previous block, right? This Merkle root, as we call it sometimes. I take the time, I take the block's ID, I take the version number, because this is kind of useful to make sure everyone's writing the same version of Bitcoin. And I take a random number used only once, otherwise known as a nonce, and I run it through a hash function, see it up top, and I get a result. So nonce 1 gets 6b, whatever. And then I say, oh, great, I can't add the hash function until I get a certain number of zeros in front. I can't add a new block to the blockchain until I get a certain number of zeros in front. So I run it again, and I use a different random number. 12590, and I still don't get the zeros I want, right? Isn't that frustrating? But then I get really lucky. I choose 2307 as my random number. I put all the stuff from the previous block in the blockchain into that input, which is like the hash basically. And boom, look at all those zeros in front. Let's say the difficulty level is 5 zeros. Well, I just got a bunch more. Cool. I can now add my block to the blockchain. So again, by producing an output that matches a certain number of zeros in front, by sending random numbers with the previous state of the blockchain through a hash function, I'm then allowed to add new blocks. But there's some problems with this. So again, this is just a kind of visual innovation, not a particularly great graphic, but you can kind of see what's happening, right? So I'm adding all this stuff together. That's the random number. That's the hash is the previous block. I have to prove that I'm matching, in this case, 4 zeros in front, but it could be, I forget what it is now. It could be like 12, or I think it's 12 right now. I'm not entirely sure. And then if I do it, then I add a new block in, and that block records the nonce, so everyone can verify it's a new block. So again, it's publicly verifiable. It connects to the previous block through the previous hash, and it has all the transactions in it. And so let's talk about how those transactions get in it. Well, maybe we cannot. Maybe we should do this. This is a little bit simple, but we'll do this again first. So this is literally, again, like if I have a blockchain, you can see that this is the number, all the transactions that people sent, and there's this little thing I want to point out, which is this is the guy that mines the block. Remember, he gets a reward. The Coinbase transaction is recorded who gets the reward as well. That's the Coinbase transaction. And you can see that each previous transaction, right, they're all linked together. So this is the hash of this one. That hash is the previous transaction of that one, which is then in turn the previous transaction of, this hash is the previous transaction of that one. You have the nonce, you have the block number, and you have all the transactions and who got the reward. So it's pretty simple. And if things go wrong, you can easily detect it. I won't go through that in detail. And so what happens is what I've described is the process of what's called Bitcoin mining. So I'm just mining this over and over again. I'm running this hash function over and over again. And I'm producing valid blocks. And I'm producing a block here, a block there, a block there. Maybe I'll skip through this real quickly and just explain a little bit how it works. And then what's happening is that the longest blockchain wins the consensus. And when I send, let's say I'm going to send you some money, I scan your QR code, I send a transaction out. There's a peer-to-peer broadcast system beneath the blockchain. And that peer-to-peer says, here's my transaction. It sends it out to all these people that are running this hash function. These people that are running this hash function on the computer are called miners. They're doing what's called Bitcoin mining, which is just literally running this proof of work hash function again and again. And then what happens is that the miner collects all the transactions that they hear through the peer-to-peer gossip protocol. When they get enough transactions, they put them in a block. And then they keep mining and they keep mining and they hear more transactions and they get more and they put them in another block. Now, what's a problem that could happen? You have a peer-to-peer system. Everyone's running these mining functions in parallel. They're putting them in blocks. Well, they might not agree, right? So these people might have a different set of blocks, right? So because they make peer-to-peer systems, networks are not magic. They don't all synchronously gossip to each other at the same time. They're asynchronously gossiping, right? So by virtue of asynchronously gossiping, there's going to be some timing differences. All these guys will get the same set of blocks over in the US, while over in China, they get a different set of blocks. And they can even have, so the question is like, I add a block in because I want that Coinbase reward, but you could have the situation where I put one block in and then I put a new block in, right? Because I look at the hash in my previous block. But over here in China, they minted a whole nother block, and then they put the new block in, right? So what this means is that you've had what's called a fork. So you have people mining independently, adding the same transactions in, but different people have essentially ran the proof of work a different amount of times, and some people have more blocks than other people. Maybe they even have different transactions. So the question is, what's the one true version? And how Bitcoin works is because, remember, these blocks are publicly verifiable, that when you try to do the consensus, the person that has the most blocks wins the consensus, right? So let's say we all agree about block 0. Well, let's do this one first. We all agree about block 0. We all agree about block 1, but then the Americans produce block 2, and the Chinese produce block 2. We actually agree. The Americans and Chinese agree on block 2. But then the Chinese produce block 3, right? So what happens? Well, if you're doing consensus, and you check who, everyone says, I would like to be part of the consensus. You look at how many blocks they have. You can publicly verify those. Remember, just by taking the nonce, running it through the hash function with the previous state of the block. And the Americans lose because the Chinese have 3 blocks. And 4 blocks, the Americans only have 3. Then you keep running, and the Chinese get 4, and the Americans, remember, when the Americans lose the consensus, they have to agree with China, so they're both on the same chain. And there's another fork where the Americans produce a different block 5 than the Chinese, right? So they have 2 different blocks, but the Chinese produce block 6, so they win, and the Americans lose again. So this is actually very common. It's very common that you have what's called occasional forking. That means there's a fork. That means there's 2 different blockchains. No one's quite sure who the right one is. So you got to let that peer-to-peer gossip run. You got to let that consensus protocol choosing a longest chain run for a while. So that's why Bitcoin is so slow. So when I send that Bitcoin transaction out, it will take like 10, 15, sometimes 30 minutes to decide who has the right. My money actually gets transferred, only gets transferred if it's in the blockchain, and determining who has the actual correct blocks takes a while because you got to keep running this until there's consensus. So it's usually like 15 to 30 minutes, sometimes longer, sometimes less. And then every once in a while, you get this like crazy situation where, let's say the Chinese do block 1 and Americans and Chinese agree, but block 2, block 3, block 4, block 5, the Americans the Chinese produce, let's say, 6 blocks, and then the Americans produce block 1, block 2, block. So they're all tied. It's not clear. Like at this point in time, we don't know who has the right chain, and only until you finally get to a point where you run the consensus algorithm, someone gets a longest chain, that you know who has the right copy of the transactions. And so that's a total pain. So sometimes you have these really long periods of time where no one knows who has the right copy and who has the money, and this is occasionally why Bitcoin is very slow. So just to repeat, and then we'll just get a question here. Well, we could do the money later. But essentially, mining is slow, but it makes the consensus fair. It gets everyone time to run the hash function a bit. And again, from a privacy standpoint, it's very interesting because this is the only algorithm we know, at least I know of, minus some interesting things with zero-knowledge proofs and proof of stake, that lets, or at least is the first one, that lets people join a consensus protocol in a permissionless fashion. Anyone can just start a computer and start running hash functions. Maybe not the environmentally right thing to do, but you can do it. And join the algorithm without revealing their identity, without having an identity.
So if I understood correctly, when people send transaction, it gets put into a pool, and then the miners pick these transactions, produce a block. So when the case of like 4K, was there a situation where some transactions are not the same and the different block? And what happened to these transactions?
They get dropped. right? So let's say this is block B and block A are different. I'm in China, my transactions go in block B. I'm in America, my transactions go in block A. I think the Chinese win the longest fork rule, so the American transactions actually just disappear. They get blocked. You have to rescind them. But you don't lose your money, right? Because the ledger counts, you only move the money if everyone agrees on the ledger, right? So if everyone agrees on the blockchain, then the money's moved. If people don't agree, then your money hasn't really moved. Your transaction goes back to the pool and then waits for the next block. And that's why it takes so long, right? Because you have to keep running this till you get consensus.
And what happened to the incentive? What happened to the reward? Sorry, if I produce a fork and the consensus is against me,
you don't get the reward. You only get the reward once you win the consensus. So everyone gets a lot of money if they get it right, and you get none if you get it wrong, but you statistically, because it's a hash function random, you have some random chance of getting it right depending on how many CPUs you throw at the problem. Now, there's a very clever attack on this consensus algorithm. What is it? Can you guess of one way you could break this consensus algorithm? Like, what's the problem with it? So I think I've sent my money into Bitcoin and to, let's say, Leonard. How do I know I've sent it to Leonard or not? Well, I check the blockchain. But what's a problem? There's a big problem with this consensus algorithm. It's not so big, but it's trouble. It worries people. Say again? Privacy, yeah, there's no privacy in it, so everything's in public. You don't know if you're the right fork. So we could have a situation where I believe in the right fork, the whole world believes in the right fork, but there's some guy, let's say the NSA at Fort Meade, has been secretly mining blocks since the inception of Bitcoin, and they've built this huge long chain, which is totally different than your chain, than everyone else's chain, but they would have the longest chain, they would win, and they would revert all of the transactions, which could be from 2011 if they were building their chain since 2011. It's a kind of crazy attack. No one thinks it's happened. And the weird thing is the more Bitcoin grows larger, the harder that attack gets. And this is related to the printing of the currency. So again, this proof of work, also called solving hash puzzles, is what is behind Bitcoin mining. But you have something called inflation. Remember, you have these coin-based rewards. I win the hash puzzle, I get some money, cool. And the amount of money you get halves every so often. Right? Currently, it's based on number of blocks, but more or less every 4 years. So that amount of money lowers the inflation rate. And this was done, I don't really know why exactly this was done. It was done technically in order to make it harder and harder, so that more and more hashing power was required over time to verify Bitcoin transactions, which means that the longer Bitcoin runs, the harder and harder, there's so much computational power put in it that becomes more and more hard for anyone new to basically be like, I'm going to throw tons of CPUs at this and break the chain. Right? So that's like the goal is to defeat that NSA attack, and the amount of Bitcoin in circulation goes down every about 4 years. So every 200,000 blocks. And this is interesting. So this is all people say, why? We'll do the question in 1 second. Everyone says, why does the Bitcoin price go up? Well, assuming demand is constant and supply halves, in basic economics, the price should go up. So what's kind of fueling the Bitcoin price going up is this kind of relatively predictable constriction of the supply. So now, if less people use it, no one cares about it, doesn't really matter. But assuming that demand stays constant or grows up even, then the price should go up every halving. And just so people know, I think the halving is like April this year, so that's why Bitcoin is going up. And then the other thing with Bitcoin is only so many coins, so that in a lot of other cryptocurrency systems, new coins are printed constantly. So you could have a system like Ethereum where you basically say, oh, we have these validators, we're running a proof of stake system, and then we just kind of mint new tokens based on some game theory rules, or just kind of like Cosmos because you feel like it. This leads to more coins being in circulation, which basically means that the supply goes up. But if your supply remains constant and it's constantly going down, the demand, assuming it remains constant and the supply is going down, it should go up. So that's sometimes why people call, that's why people say Bitcoin is like gold. Okay, so that's the explanation of Bitcoin. What's your question? Yeah, that's a pretty dangerous attack. Yeah, well, that's why the difficulty is not based on like the clock. Like it's not based on like April 2024. It's based on the number of blocks. So even if I'm the NSA, secretly by myself with a giant GPU complex, building a big blockchain that was going to win the consensus, because the reward halving happens that's just hard set into the code, their chain would have to also hard set that in. Otherwise, there's like essentially a version difference they can't merge. So that's also why upgrading Bitcoin is so complicated, right? Because all the miners have to agree to kind of run the same software, right? So you've had these big fights, like how big should the block be, and what's called segregated witness, and these kind of fights. And so that's why the Bitcoin code base is kind of what you call ossified, which is why a lot of people create new cryptocurrencies, because you can't, you have to kind of agree with everyone's code, right? So I could create, and actually people have done this. I can say, I believe that the Bitcoin code should do this, have bigger blocks and less inflation or more inflation. And I can just fork the Bitcoin code and create a new Bitcoin, which in this case would be Bitcoin Cash. But then none of the Bitcoin miners will accept it. So there's a point up until where I fork the code where everyone agrees, and then my fork goes off. And then my little set of miners, like this is literally like, we will just never get consensus because I changed the code. So Bitcoin Cash miners go this way, and then Bitcoin miners go this way. And then you say, well, what's the difference? It's more or less the same code. They did some minor changes. Well, the difference is that coins on this tree will no longer match coins on that tree. The transactions don't match. Maybe the inflation rates change, the difficulty rates change. I don't know, like what you just suggested. And then the market will have a different price for this Bitcoin versus Bitcoin Cash. Or let's say this is the NSA. NSA is making a really big chain, but they changed some code. So who's really going to want NSA coin? Well, maybe no one, right? People will want the real Bitcoin. This is the kind of game theory going on. That the market determination of price should to some extent determine how valuable a fork is, or an altcoin, which is just, an altcoin just like starts somewhere totally different, but can do different things with consensus, or different things with privacy. Does that make sense? That like they can't just change difficulty because then they would be running a fork, and that you have to have the difficulty set by blocks, not by clock time. So, I mean, you have to admit, like it looks a bit amateur, but you're like, oh, there's some clever parts of this system. So one of the not so clever parts of this system is unfortunately the privacy elements. How much time do I have left? I'll speed this up. Okay, I'll speed it up. Okay, so privacy in Bitcoin works with what's called unspent transaction output sets. So what this means is that how I record blocks in the blockchain is honestly a little funky. We'll go do smart contracts later. So again, I send a transaction, and everyone is identified by a key, and that key is considered a pseudonym, right? So you don't put your name on the blockchain, you don't put your ID on the blockchain. Maybe your cryptocurrency exchange might ask for it, and they can attach it to your pseudonym. But your key is essentially a pseudonym. And then this is what Nakamoto said about privacy, that essentially a new key pair, this is kind of, a new key pair should be used for each transaction to keep them from being linked to a common owner. However, some linking is still unavoidable with multi-input transactions, which necessarily reveal that their inputs are owned by the same owner. The risk is that if the owner of the key is revealed, linking could reveal other transactions that belong to the same owner. So they have this kind of like pseudonym-based privacy. You say, okay, every time I do a transaction, I'm going to generate a new key. So that is a little bit problematic insofar as it is less anonymous than, is actually less anonymous than cash. So let's think about what does anonymity mean in terms of transactions. A transaction is typically anonymous if no one knows who sent or received the transaction. Now, there's kind of weaker versions of this. You could say a transaction is private if what amount was sent and what was purchased, perhaps, are unknown. And you could also do more complex unlinkability. You can say maybe the sender is unknown, but the receiver is known, or so forth and so on. And we're not going to, we're going to assume that there's no out-of-band linking to identity information by your wallet or cryptocurrency exchange. We're just going to look at the technical system. So we're saying, so Bitcoin is anonymous. Well, it's not anonymous because A, the transactions are all in public. They put in the chain. They have to be public because that's how you figure out no one's minted new money. If they were private, then maybe someone just creating new money out of thin air. How would we know? And the sender and the receivers are recorded, but they're recorded using pseudonyms. So the way a pseudonym is recorded is I have a private key. Remember how keys work. And I have a private key, and I multiply it by an elliptic curve group element, and I get a public key. And I can just choose another random elliptic curve element. I get from one private key 2 public keys, or 3 public keys, or 4 public keys, and there's various ways to make a lot of different public keys from a single private key, and that's fine, and that all works. So it's okay. It's easy to create pseudonyms, but the problem is really the metadata. So we have the public reusages of addresses in Bitcoin and Ethereum. So I'm sending money, you're sending money, right, from one address to another. And let's just look at how this works, and we'll talk about it a bit more. This is like a very classic way to discover who's sending money from one person to another. It's called what's called transaction graph analysis. So again, all this is public. Everyone has pseudonyms. So how do you break it? So how Bitcoin works is that I send you money, but then the spare change goes back to myself. It's a little strange, but that's the reason is like essentially like each key has the amount of money in it, and Ethereum works a bit differently. But how Bitcoin works is that all of the money goes to the person, your recipient, and there's a change, and the change goes back to you, typically. So it's a little bit easier if you go through an example. So I'm Joe. I have 1 Bitcoin, right? And I'm going to send it all to Alice. So I send Alice 1 Bitcoin, and that's a transaction. I send all my money to Alice. Then Alice basically, but she only wants, I only want to pay her 0.015 Bitcoin. So she gets, remember, 0.015 Bitcoin, and then the spare change, which is most of my money, goes to, is not spent, 0.0845, and that goes essentially back, right? So Alice then gives Alice is taking, I got that backwards. Alice is taking 0.0845 and Bob gets as spare change 0.15. And there's also what's called a transaction fee, which goes to the miners. This is like an order for building this block that gets in the blockchain, and that transaction fee is some utterly tiny percentage. And then Bob's new key, right, because he's minting a new public key, Bob gets 0.015, okay, and he sends it to, let's say, Gopesh. He wants to send 0.01 to Gopesh. Then he gets 0.0045 as change. And again, you have to subtract a small transaction fee. So what you can see happening here is that effectively, like, I'm sending transactions to people, right? This, I can send all of my money, as we did in this example. I can send part of my money, in which case I get change returning to me. And then we can just follow the chain of who's spending money to who and who's getting the change back. So even if this change, the key point is that this change can be used to de-anonymize you. So no matter, because you can basically say, there's a very simple attack here. We'll just go to it. Oh, that's Monero. Where's my slide for the attack? Left it out. So not only are you reusing addresses sometimes, sorry, I have to find my, no, that's all Monero de-anonymization. Okay, well, I don't, anyway, sorry, I had a slide on it. I think I left it out. But effectively, like, following a transaction graph can identify the people behind cryptocurrency transactions. Transactions always have more than one address. It is likely, given a transaction has typically one address sending to at least two addresses. You can actually send more, but let's say at least two. It means that at least likely two addresses are controlled by the same person, including at least the input address. If one output address has never appeared before, because remember, people publish their receiving money addresses, it's more likely that it's what's called the change address. You're getting the spare change, and that address is linked to the same person doing the transaction. And this very simple heuristic can de-anonymize all the pseudonyms, right? Because what you do is you just say, well, do most people want 2.117 Bitcoin for a transaction? No, most people, they'll say, I want 5 Bitcoin, I want 1 Bitcoin. They'll want some round number, right? So it's a very simple trick. You can just look at the numerical precision of who's sending Bitcoin around to other people. Not all the time, right? So maybe they're denominating their purchases in dollars or whatever. But typically, if there are two outputs and one's a big, fat, this is very simple. One is a big, fat, round number, and the other is some change. It is likely that the big, fat, round number, such as 5, is going to the recipient, and that the number with a bunch of little spare change in it, 0.21, 0.117, is going to the sender. And all of a sudden, you've just broken Bitcoin's anonymity. And it's very simple heuristic. You said, well, the sender, the pseudonym, this pseudonym here is linkable, that pseudonym over there. This key of the sender is linkable to this change key. And you can just keep repeating this process over transactions again and again and again, and you can basically nail who's transmitting to who. So the problem is by leaking, even with one-time keys, by leaking the key and leaking the values of the amount, you can effectively de-anonymize Bitcoin pretty quickly. So does that make any sense? It's like sort of obvious, I know, but somehow Nakamoto didn't really think about it, right? So this is what led to, and also there's all these other tools, I'll just mention them quickly, really easy to de-anonymize Bitcoin. One is that most de-anonymization also can happen outside the blockchain. Merchants publish as QR codes usually on their website or addresses their public keys. So I want to know, like, does this key belong to darkmarket.com or KU Leuven or whatever? I just like go to KU Leuven's website, and I look at their key, I look up the change, then I can see like every person that's donated money to KU Leuven, or every person that's donated to or bought something over darkmarket.com, right? This is all like once you publish your recipient key and you link it to your identity, for example, on a website, on a payment server, boom, you've just linked yourself. And often people, this is actually how Silk Road got taken down. People just leave their Bitcoin address in like a public discussion forum, right? So maybe you don't have a big website that says darkmarket.com, but like on some like email list or in some email, you say, oh yeah, here it is. And that email is actually public, or that mailing list is, the email is intercepted, or the mailing list has in the case of Silk Road, an agent on it. Boom, they can just link you to that transaction. They can link the email address to that transaction and follow the email address. How often, I mean, what other things do people do to link transactions? And it's not just law enforcement, right? There's a whole industry, including often cyber criminals, of linking Bitcoin to transactions. So, right, so someone's like, am I, because I have a cryptocurrency company, am I rich? So there's people whose entire job is to basically try to figure out what's my Bitcoin address. They try to hack into my phone, happened 2 or 3 weeks ago. They try to break into my Twitter. They're looking for this Bitcoin address, looking for my keys. And one thing they're always looking for is like where I am, right? Because sometimes people sometimes they get kidnapped over their Bitcoin and they hold them hostage and want to beat them till they give them Bitcoin. And 1 second, so you can often track people down by their IP address. Right, so Bitcoin uses a peer-to-peer network, and peer-to-peer networks broadcast the IP address. So when I use a wallet with Bitcoin, now I'm broadcasting my key and my transaction size. I'm also broadcasting, because it's just how the internet works, my IP address. And my IP address, like 128.29, whatever, I think this was covered last time, leaks my kind of general geographical neighborhoods. I can say, oh, he's in Leuven, he's in Belgium. And so this is a real problem. And you can just take an IP address, look it up on a public website, like what is my IP address, and discover where I am. Yeah. Yeah, there's been a rash of break-ins like about 2 weeks ago. Because I get alerts on my phone when someone's trying to break in. So for example, like if someone tries to hack my Twitter account, I have alerts set up. So I say, okay, I had someone try to log into my Twitter account and from I think Ukraine. If someone tries to hack your phone, they often call the phone company, because your Twitter account or your iPhone account or your Microsoft account is often protected by two-factor. Two-factor, unfortunately, being via SMS. So they call the phone company, say, hey, I'm Harry, I lost my phone. Can you just give me a new SIM card? And they'll give you a new SIM card without checking your ID because they're lazy or they're corrupt. And then some random guy will have your SIM card, and he uses it to try to reset all your passwords and get into your Bitcoin. There's a whole industry here. So law enforcement does this as well. But I mean, there's also, nation states do this, right? North Korea funds most of a lot of the ransomware attacks for Bitcoin. The vast majority, like 95%, I think, are North Korea. So North Korea is funding their nuclear program using ransomware attacks from Bitcoin. So they say, okay, we hack your school system. We're going to lock down all your emails. And unless you give us 5 Bitcoin, then we won't ever let them go. People do give them 5 Bitcoin. It happens all the time. And then they use that to fund, because they're under sanctions. They have problems getting money to fund their nuclear research program. So it's not just like cyber criminals in Ukraine. That's what happened to me. It was more like often these attacks are nation state level. Yeah? Yeah, once you get, you can do that very simple transaction graph attack, and it's probabilistic, but it's pretty good. And you can, once you get someone's address, you can more or less de-anonymize them with like pretty high certainty. It depends what size computer they have, if they're running the right software. So if you're like an academic, let's say, I think the paper that first did this, I think was maybe Sarah Meiklejohn at UCL. Yeah, a few days. I mean, it's not really that complicated. The Bitcoin blockchain is big, but it's not like impossibly big, right? So a reasonable size computing center can do large scale de-anonymization attacks pretty quickly. So it's definitely, you don't need nation state level like GPU power. You would need that to break blockchain consensus, but actually just tracing transactions, you feed the heuristics into the blockchain, to your computer, you feed, the whole Bitcoin blockchain, I forget how big it is, but it's not so big. It's like maybe a terabyte or so. Fits into a hard drive, and you can just run through it and get those transactions out. It's pretty dangerous, right? So it's a real attack, really happens. There's people kidnapped, all sorts of crazy stuff, law enforcement arresting dark market criminals. It's like all over the place. And so, I mean, you can do things to defend your IP address. So Leonard covered this. You can use a VPN, but then you can do traffic analysis on the VPN. You can use Tor. Tor and Bitcoin are not great matches insofar as that you'd have to reset your circuit to get a new IP address, which is fine if you're willing to wait. I think Tor's default is 10 minutes for a new IP address, but if you're doing like multiple things with that IP address, then it's not great. Mixed nets, I would argue, which is what we do, are slightly better insofar as that each transaction would by default get a new IP address and be ideally somewhat traffic analysis resistant. I won't go into that, but effectively the way you want to think about using a mixnet or Tor is that you put your wallet over here, you run mixnet or Tor in the middle, and then you put a blockchain over here. So it's not even that complicated. It's like you have a little secure or anonymous tunnel between you and Bitcoin. But doesn't really matter if you have a secure tunnel because you're still putting all the stuff on the blockchain that someone can just de-anonymize it by looking at the blockchain. So what you need is some privacy on the blockchain. The first way people thought about privacy on the blockchain is this technique called mixers, which are not mixnets, often confused, but it's a whole different thing. And a mixer basically sends transactions from multiple addresses into a big pot. That's the way I think about it, called a mixer. And they charge, these are for-profit entities like Samurai, they charge up to 25% of your cash for mixing it together. And then they output it. So I'm going to send, rather than send you 1 Bitcoin directly, and I get my change back, my point, whatever, 21177 that identifies me. I send 1 Bitcoin to a mixer. A bunch of other people send Bitcoin to a mixer. So you send tons of money to 1 address. That address waits a long time. That's really all it does. And then it sends you back your change later and sends the money to the recipient later. And so the theory of a mixer is that, well, if enough people send enough transactions in, and there's a long enough delay between the change and the money being spent, this would mix the traffic. And it does not really work very well. So it doesn't work very well because, again, statistics are more powerful than people think. You can just wait a really long time. Over time, you de-anonymize things. And there's a really big problem with mixers, which is there's this thing called the mixing address, right? So you can see that you're using a mixer, right? So typically when you use a mixer, it means you're trying to hide something. You're about to do something illegal. North Korea, for example, uses a lot of mixers. Those mixers like Tornado Cash get shut down. And so you can determine if a coin has been used by a mixer or not by just looking for the address of the mixer in the transaction graph. And that means that the coin is, the term people use is tainted coin. So maybe you do use a mixer, but then no one's going to touch that coin because it's been through a mixer. And then the mixer itself can usually be de-anonymized. So what you've seen is using these statistical transaction graph analysis techniques, particularly US law enforcement has de-anonymized and arrested like the owners of most mixers. Right. But then it's kind of weird. Do you really want a world where everyone can see everyone else's transaction? I mean, that's kind of odd, right? So even on a CBDC, that's odd. And Bitcoin, it's kind of odd. seems like, money is kind of private. We should have some form of privacy in money because that was useful, not just useful for illegal things. Yep.
So you said US law enforcement arrested the owners of the mixing platforms or the people who mix?
Both. Usually the mixing platform goes down first. Yeah? So this is more in the financial regulations, but sending money back and forth, at least under US law, requires what's called anti-money laundering checks and KYC checks. KYC means know your customer. The whole point of this is what's called sanctions compliance. This means the US may have beef with, for example, North Korea, so it's illegal to send North Korea money. And the way they detect if you sent North Korean money, say, well, you have to attach an ID to everyone, right? Now, usually the US ignored, which is why North Korea started ignored Bitcoin transactions for a very long time, but now, since North Korea is using them a lot, they basically will say, okay, if we believe you're running a service, which is sending money back and forth, that service is what's called a money transmitter. In order to operate a money transmitter, like if I just can't make my own credit card or my own bank. That's like a banking license. You have a money transmission license, and that license requires you to basically ban people on sanctions list. So the law that you're breaking is you're not banning people on sanctions list. And you can say, oh, I didn't know, or it's not really a money transmitter, but fact of the matter, if North Korea is going through it, the US views it as a money transmitter and will therefore arrest you for running, a very small, the smaller charge would be, maybe unlicensed. I'm running an unlicensed money transmitter. And most cryptocurrency services are considered unlicensed money transmitters. And the US typically doesn't care too much until someone like North Korea uses it and they're like, oh, you're breaking sanctions. And sanctions typically have like 5-year jail sentence minimum, sanction compliance breaking. And unfortunately, because the US is a big country, they force every other country to do it, except those obviously under sanctions. Yeah, I mean, it's very peculiar, but all money definitely falls under sanctions, and it depends. Like, sanctions can be very peculiar. You could say these individuals are under sanctions, like let's say Putin's family, I think, or Putin himself are under sanctions. Maybe not all Russians, or maybe only Russians in this area, like occupied Ukraine are under sanctions. So again, the granularity changes, not just whole countries. And then like how the sanction works changes. Some sanctions are very harsh, like North Korea, like you can't send them money, you can't send them anything, even if they're starving to death, you're not really supposed to send them like, medical supplies. But then you have other places where it's like, okay, it's okay you shouldn't send them money, but it's fine to like, send them medical supplies, but you shouldn't send them like missiles. You shouldn't sell them missiles, right? So because the missiles are illegal, because it's a sanctioned country. So it really depends. Different countries are the sanctions are pre-digital, so it's all written down and pre-digital thinking. But typically, the way that the sanctions that are typically enforced most clearly are not like shipping missiles. That's usually detectable at borders, or shipping gold or medical supplies. You can distinguish these by looking at the kind of border guards. You'd find those. But money is really hard because it's all digital. So you don't know if this guy behind the Bitcoin address is in Ukraine or North Korea or Belgium. You have to so there's vast amounts of money spent by nation states in Europe and the United States doing transaction graph analysis to determine who owns what address and who's sending money to who. Does that make sense? Yeah, sanctions regimes are sort of crazy. They probably need to be updated at some point. But let's talk about alternatives. So this, weirdly enough, is similar to Bitcoin, which is just some anonymous dude published something called ByteNote. And he said, hey, let's not use Bitcoin has all these privacy problems. So let's fix them. And the basic concept behind Monero is not to use normal digital signatures, but use something called ring signatures. The way you think about a ring signature, it's a group, but group signatures typically have like some manager for the group. And ring signatures basically means any member of the group can sign the transaction. And the real signer signs once, and everyone else is a decoy. This is the strategy that Monero uses. And it's a very hacky code base, but has a high amount of usage. So again, what's the problem with Bitcoin is all the addresses are public and no one can stop you from reusing the same address. So Monero says, we will never let you reuse the same address. Each address has to be new. And how does Monero do that? It uses something called stealth addresses. What is a stealth address? Do people know Diffie-Hellman? Okay, so the concept behind stealth addresses is really simple, which is I don't publish my address, which is the hash of my public key. Forget about it. I publish an encrypted public key to the blockchain. So I publish an encrypted public key to the blockchain, right? So everyone's addresses are essentially encrypted using Diffie-Hellman. Now, what's the obvious efficiency problem here? Well, in order to see if anyone sent me money, I have to scan the entire blockchain and keep trying to do a successful Diffie-Hellman with each address until I discover that, goes through and that's money's for me. Because I have to try, I go through each block in the blockchain and be like, decrypt this address, decrypt this next address, decrypt this third address. And at the end, I have discovered that I have 3 or 4 addresses in there and I take that money, right? So the addresses are encrypted using Diffie-Hellman, which is cool, but it's pretty inefficient. So that's what's called a stealth address. And this is the ring signature trick. Every transaction is sent to multiple addresses via ring signature. So again, in Bitcoin, the basic paradigm is I send you money, you send me change. Maybe I send money to 2 people, but I still get my change back. Unless I'm very careful with how I spend my Bitcoin, so I never get change. I can always get change of 0 back, but even that can be used to identify me. So how Monero works is that there's never one sender. There's always what's called the size of the ring. A number of people send money to a person, and it's at least, I forget, the minimum keeps changing. I mean, for a while it was 2, which is pretty bad, but now it's like 11 or 12. So this is a bit out of date. But imagine we have 12 people sending money to someone. Now, only one of them is the true sender. And the way Monero works, it kind of automates the process. So I want to send money to someone. So I have my stealth address. I know their stealth address. I send them money. Cool. And then the kind of Monero software automatically picks up to 3 or 12 or whatever other people, and they automate the sending of 0 and one person sending the real money. But on the chain, it looks like there's a bunch of people sending money, so it's hard to determine who sent money to who. And of course, the reason why that works is because, Bitcoin values are visible, right? The amount you send is also not encrypted. So I'm going to send someone some money, and I send this person 1, this guy sends me 10, and that's all can be used to de-anonymize me, even if I'm using encrypted addresses. So Monero also hides the transaction values via encryption. But you got to make sure it all kind of adds up. So what kind of encryption would you use? Everything's encrypted, but you want to make sure that you're not overspending, or you're spending the amount that's in your wallet. So what do you use? It's a kind of encryption that's very simple. Maybe you got homomorphic encryption. Right? So homomorphic encryption can say, I have an encrypted value, I can add stuff, I can subtract stuff. We can use something called range proofs to prove that I've not gone beneath 0, right? That I'm less than the total amount of money ever printed or the total amount of money in my wallet. So some combination essentially, so I should have had an explanation of range proofs here. But essentially, you hide the address using Diffie-Hellmans, and then you hide the amounts using homomorphic encryption. And then this kind of enables this crazy thing here where a bunch of people are sending homomorphically encrypted values of which 90% is 0, but 1% is the real spender, to an encrypted address. And the theory is that will, and this has never been academic, this wasn't an academic paper, it was just a thought that the guy coded up, that this will break transaction graph analysis. Now the question is, does it break transaction graph analysis? And the answer is, not surprisingly, no, because you're still leaking a whole lot of information. So, you know, you can basically look, this is like the most simple Monero. There's many techniques to break Monero. This is probably one of the most simple ones. You can basically say, okay, who's sending money to who, and just look at it over a long stretch of time. And if you look at it over a long stretch of time, you can sort of guess. So I want to guess who sent money to this guy. And I have 3 suspects, right? And now, remember that the people that send 0 are automatically selected by the software in a randomized way, which is not, so you can't just guess who it's going to be. There's no way to look at the code and figure it out. But essentially, if this guy, if you send money, right? So if this guy sends money to this guy, or possibly sends money to this guy, but then also possibly spends money to this guy, and this guy might spend money to this guy, but also send this guy, well, honestly, like, because you're not supposed to reuse addresses, what that means is that these addresses have been randomly selected to send the money, to be the cover traffic, let's say, for the transaction. So you use a simple technique, deduction technique. We just look at the transactions over a long period of time, and you say, okay, well, maybe it's one of these 3 people, but since this guy sent some money later, and this guy sent some money later, and we know by the rules that you're not supposed to reuse the address, then boom, it's this guy that actually sent the money. We may not know by how much, but we know that's the active address. Furthermore, you can just like look at how old the address is, right? So again, like, you know, because there's no, I mean, they keep changing the software, but the question is, you only have so many Monero addresses. So if you see 3 transactions going into a Monero address, so it's good that Monero encrypts the value and chooses random addresses. I mean, this is all nice, and the address is hidden. But you can also just look at, like, you can do a very simple timing attack. You can sort of say, well, this address appeared 2 days ago, and then money went here. But these other addresses, no one's used them for a really long time. So it's more likely this guy sent the money, and this guy that hasn't the address appeared 3 months ago, and this guy that spent it 2 years ago probably didn't spend the money. So there's like combination of like pretty simple heuristics over time can break Monero. It's, and this particularly, you know, you can, and then when you add like out-of-band information, you're like, oh, who bought this drugs at Alpha Bay? And you have like 3 suspects that bought the drugs. And you know kind of when they bought the drugs. Maybe you caught the drug shipment, and the drug shipment was caught like 3 months ago. And you look at like Alpha Bay's account, and you say, well, who sent the money? Like 3 months ago, there's only one guy. That's probably the guy that bought the drugs account, right? So the timing analysis isn't always as choose the most recent. You can use like out-of-band information to kind of guess who's sending money when. And so that's a pretty big danger with Monero. So the obvious answer, how much time do I have? Okay, so we'll speed through this, even though it's a little bit complicated, is zero-knowledge proofs. So zero-knowledge proofs, pretty complicated. But the whole concept is I want to prove I have some money, but I don't want to reveal how much I have. Okay? And rather than like hide it by this thing called this decoy traffic or decoy spending with Monero, I actually just give you a mathematical proof. And that mathematical proof then proves that I sent you the money, that I haven't overspent my money. If that mathematical proof has to not reveal my address. It has to be and we'll go through it, but it has to not reveal my address. It has to prove to you that you got the money, but it can be recorded on the blockchain to prove that the amount of money isn't just being, that there's no double spending. So you want to solve the double spending problem without revealing how much you're spending or who you are. And it involves some pretty complex cryptography, but it's general purpose stuff, which can be studied in many other contexts, and is used on not just Bitcoin or Zcash, but Ethereum and other blockchains. And the general concept is that I have some money, which is like Bitcoin, which is public, and that's called transparent. And then I want to kind of like hide it. I want to hide the value, and ideally the recipients and senders. This is called shielding. And so when someone says amount is shielded, it just means it's hidden via zero-knowledge proof. And then I de-shield it, and I can send accounts, I can send public money into what's called the shielded accounts, but the shielded accounts are again, they're proofs, they all look the same, so it can be thought of as like a big mixing pool. It's a shielded pool. I can de-shield, I can send money out the shielded pool into the non-shielded pool, and I can send money privately from one shielded member to another shielded member without revealing anything. And that's pretty amazing. Seems like it should be impossible, but the magic of zero knowledge lets it be possible. So I don't, unfortunately, have slides on zero knowledge in particular, but let's go through the properties and then we'll discuss zero knowledge. So the concept behind Zcash is also used by a lot of other systems. It's called decentralized anonymous payments. And so nothing is revealed besides public information, right? But you can't spend more money than received or than that's created. And you can't manipulate transactions on the ledger. So these are the properties. So I can't change, like, you have this Merkle tree where everything's given a hash. I can't change. You want to get the same properties as a normal blockchain. You can't spend more money than you have. You can't double spend. New money can't just be minted automatically. You have to have some inflation schedule around proof of work or proof of stake. And you can't change transactions, but you don't want to reveal any information from the shielded pool on the chain. So how that works is you use a proof as a zero knowledge called ZK Snark, one exciting name. And it's a non-interactive zero-knowledge proof. That's what NIZK means. You'll see that a lot in crypto papers. And what a snark means is a zero-knowledge. Snark is succinct, which means just means it's small, not huge. Proofs can be very huge. Non-interactive, which means I can prove without talking to you. You just give, and I'll explain a little bit how to do that. Argument of knowledge, so you prove that you know something. The thing you're generally proving in zero knowledge is I have sent you this amount and you have received it. So let's go through this really quickly. So how, let me see, maybe my slides explain it. So how zero knowledge works is you have in general, you have what's called a prover and a verifier. So the prover generates a proof and the verifier verifies the proof. It's a zero knowledge proof because it doesn't reveal any knowledge outside of typically true or false, right? 1 or 0. And there's an amount which goes into the proof as a random, and you get a witness. So it's like a digital signature, which is essentially randomized. That witness plus a secret value, right, produces a proof, and that proof is typically that I know the secret value. You can do very complex things in zero-knowledge proofs. You can even prove that I've ran a whole computer program, that the computer program is ran successfully. So you could input, like, your secret value could be like a whole computer program that's running against all sorts of possible inputs. But typically, it's much simpler. With cryptocurrency, you're just kind of like, did I send you money or not? And did I overspend the money? And that zero-knowledge proof basically the value you sent and who you sent it to and all that stuff is your inputs. You get a witness, right? And you can then do a game with the verifier, and the verifier gets the witness. And that game then basically proves if that you know the secret value without revealing the secret value. Okay. And why would you want to do that? Because you want to check to make sure the money actually went through and that all the money adds up, that you haven't minted. Remember, you haven't spent money you don't have. So it's kind of what you would call a double spending check. So how this works is it works via what's called commitments. So a cryptographic commitment is like a box. The easiest way to think about it, I give you a box, and in that box there's a value, and it's secret, and only when I give you kind of permission, via giving you like a key or a value, can you open that box and then know what the secret is. So I can reveal it later. Right? That's how I think about commitment. So typically what we're committing is I have a bunch of coins, and the difference between Zcash and Bitcoin is, and this is a bit similar to eCash, people know it, but eCash is centralized and this is decentralized, is I have a coin, and that coin has a serial number. And that serial number proves that I haven't double spent it. It uniquely identifies the coin. But I don't want to give you the serial number of my coin because that reveals that I have the coin. So I have a coin. Let's say the coin's worth 1 Bitcoin, and it has a serial number. And that serial number, what I do is I do this commitment trick. All the commitments are just hash functions. So I put in a serial number and some randomness, and that produces a commitment. And then I can reveal that commitment. I can prove that I committed to it at this time. If I kind of, let's say this is a hash function, and I can run this commitment randomness and serial number again through that hash function to get the same commitment. So I have a wallet, in my side of the wall, there's a serial number, there's a randomness, and I can basically say let's say I have $20, I have one $10 bill, one $5 bill, and 5 $1 bills. So that's 7 coins, that's one $10, 5 $1, and 1 $5 coins. I give each of those coins a serial number. There's more complex with you, I'm just kind of giving you the intuition. And I make commitments, well, actually, sorry, I did 8 here, to each of these coins. Let's say we also have a coin of 0, right? There's no reason you can't have a coin of 0, it's fine. So I have 8 coins, 5 $1, 1 $5, 1 $10, and 1 of 0. And for each of these commitments, I kind of keep in my wallet the serial number and the randomness. Oops, sorry, that didn't come out very well. And then, so I do that commitment. That was the first commitment. And then I guess the key is I have to prove, again, that, this is my coin, this is the serial number, and what did I leave out in my initial commitment? I said, here's a bunch of serial numbers, and here's a bunch of randomness, but I left out the value, right? Remember, I have one coin, which is $5, and the coin could be $1, could be 0, could be 10, could be 1,000, whatever. So I do 2 commitments, right? I commit to the serial number and the randomness. Then that gives me a commitment K. Then I put my commitment inside a commitment, and I commit to it with value, V. That's the denomination of the coin. And I get another bit of randomness. And then what I want to do is when I create a private coin, so I'm creating a private coin, I want to say I am spending this much, let's just say Bitcoin, it can be whatever, dollars, Zcoin, whatever. I'm spending up to V. And here's a commitment I'm sending up to V. And I know, and I can prove to you, I'm not going to show you the serial number, but I can prove to you that I am using a coin with value V, and the way I prove it to you, I'm not revealing the serial number, I'm not revealing the value, but I can prove you using a zero knowledge proof that this randomized witness is consistent, shows that I actually did that commitment. And then how you then spin these darn things is, again, you basically have to have an address, right? The address is a public key and a secret key, similar to what we called stealth addresses in Monero. And then, I would like to spend money, and I want to prove that I sent it to you. So how would I just minted these anonymous coins. I want to mint them to you. I want to give them to you. So I throw your public key into the commitment. Right? And then basically, so I'm sending you the money. I want to hide the serial number. Right? The serial number is unknown. And you have this kind of branching. So remember, this is the serial number which is not known to the sender. This is a PRF, pseudo-random function, which is otherwise known as a block cipher. Right? So if I would like to receive this money, my secret key goes into a block cipher, and I have this serial number. Let's say the serial number is actually randomly generated. That's how it works. And then the sender basically doesn't know my secret key, but he does this branch. He commits to my public key, makes a commitment to the public key, cool, makes a commitment to the value, and then writes that commitment on chain so we can then prove that the money was sent. And if I want to kind of like receive it, I can run this block cipher with a little bit of math here I'm skipping, but essentially I can run a block cipher with my private key, and I can get that serial number. And that serial number then belongs to me. So essentially what you've done is you've shifted a serial number, which could be $5, $1, from one wallet to another. You prove you sent it by committing to that serial number, right? And the serial numbers are owned by someone, so they're not just hanging out there. And that the sender can then basically get that serial number, and they do this by basically, I send by committing to their public key, and only the secret key can get to the serial number. So just to maybe go through it again, the coin's secrets have to be encrypted to the recipient's public key. So if they're decrypted, so again, this is why it's important that everyone in a zero knowledge based system, their addresses are essentially public key, private key, just like Bitcoin, right? And this is not, I have some randomness. I essentially need to send the encrypted secrets that the recipient can then run the zero knowledge proof. Well, what do they need? They need the value I sent you, right? They need the initial randomness, which we use to generate a serial number, but they don't know my original serial number. And they need the two witnesses, which are also randomized. And if I send you the value, I send you the initial randomness needed to generate the serial number, and I send you two other witnesses, then, and I can't send this to you in plain text. I encrypt it, I send it all to you. I can then check this commitment in zero knowledge and just say, oh, well, that's great. You did actually send me to my public key. I can show that, because I have my public key, so I input my public key in, I input this in, I input that in, I input the value, and boom, I get the commitment. So if that commitment's in the chain, I have proof that you sent me the money, right? And I can use my secret key then to generate a serial number. And the second thing that Zcash does is how do you prevent double spending? So this is cool. I'm doing commitments in zero knowledge to prove that I've sent money. But how do I prove that I haven't sent the same money twice? You have to go back to the setup. Well, remember, each value has a serial number. So the second thing you do is when I send is that there's a commitment, right? That proves the money's been sent. And I also have to, I think I have a slide on this, check that the serial number, I don't actually, sorry. You have to basically check to see that this serial number hasn't been spent in the past. That this serial number that's not double spent. So you want to do a commitment to the coin. This coin commitment basically has like what you might think of like the seed of the serial number in it. Remember? I get this seed, right? So I can say, is the serial number I received, has that been spent before? And I can check, has someone spent before by checking this commitment because the serial number is also kind of in this commitment. So essentially I have to do, I can prove via that commitment, which is again a big kind of hash thing in a blockchain, so it's not obvious. But I can use that as kind of a bulletin board to prove that I have indeed received the money. That money is of value V. It was definitely sent to me because my key kind of unlocks the commitment. And I can use this random value sent me to make sure I check to see the serial number. Has that serial number been spent before in another commitment? So there's a big problem with this system. I'll just mention it briefly, which is that every time you send money to someone, you have to write this big commitment on chain. You have to do this kind of zero knowledge game, right? The zero knowledge game, why it's non-interactive is that rather than kind of interactively checking, you just basically do a transcript of the checks, then you hash it, and that's the non-interactive part. And then by virtue of doing those checks, I can determine if the coin's been spent or not, but the fact is every transfer writes a big commitment to chain, and then you have to like check this huge list of commitments to make sure that your coin hasn't been spent before. So this coin being spent before is called a nullifier sometimes. And so the chain, as the chain gets bigger and bigger, you get more and more coin usage, you get more and more nullifiers, and you have to check them all basically because it's all wonderfully encrypted as commitments, and the serial numbers check gets larger and larger, and it just becomes very time consuming. And that's why zero knowledge proofs are slow, but unlike Monero, this is incredibly privacy preserving because there's no sender or receiver on chain. All that's on chain is a big list of commitments, which then you can use to check to make sure someone's really sent you the money or not, and that they're not double spending. But it's a lot less obvious, I'll finish in one sec, than Bitcoin, because with Bitcoin, I can just look at this hash, I get all the transactions in public, I can make the Merkle tree, I can count the hash functions, everything's very public. So it's very easy to tell if someone is double spending. It's very easy to tell that no new money has just been magically created by, for example, Nakamoto or the creators. And with zero knowledge proofs like Zcash, it's much harder because all your blockchain is this giant list of commitments. There's no addresses. There's no values. I mean, in theory, all the zero knowledge proofs should line up, but what if they don't? How do you really know? Unless you have everyone's keys, which no one does. So you can mathematically kind of prove it to yourself that the system should work, but it's much less intuitive to verify. So the nice thing about Bitcoin, everything's public and it's publicly verifiable. Zcash should be, in theory, kind of the mathematics is verifiable, but the system, even this is a relatively simple zero knowledge system, right? You can do much more complex zero knowledge stuff. It's pretty friggin' confusing, and it can't be publicly verified. But because there's not senders and receivers and transactions and stuff on chain, what does this system prevent? It prevents transaction graph analysis because it's just a bunch of commitments. So, okay, so one question at a time. You go first. Yeah, so this is where, I took out a slide on this, but there's essentially, the way it works is there's a sort of shared randomness. This is often called the trusted setup. So you have a shared randomness pool. It produces what's called a common reference string. And that's kind of where the serial number comes from. So you imagine that we have like a kind of pool. You don't really have the serial numbers directly, but you have this like shared randomness that everyone has to use. If that randomness is biased, that's really bad as well. So it's generated quite carefully. But a lot of the theories that Zcash is hacked, what they really mean is somehow this randomness is hacked. Because you have to kind of, these serial numbers are getting randomly chosen from the shared randomness, and then essentially run through like a block cipher with the key of the recipient, and that gives you the output serial number. So the reason is like if each coin had this is actually a good point. If each coin had a unique serial number, which is how it works in like classical eCash, which we didn't go over because of lack of time, then one of the problems you can use that serial number like to identify the transaction. So the way you want to think about it is you have the shared randomness, which is like the thing attached to the coin, some bit of randomness, which you can then share with people. But the actual serial number of the coin is generated by pointing that serial randomness through a block cipher, effectively, with the keys of the sender. The key of the receiver, and that gets you the output serial number. So the serial numbers are kind of like they can be checked, but they aren't like sticking to your coin forever. Because if they're sticking to your coin forever, you would have some problems. But you're trying to say, I can't give you the same coin twice. I can't give you and another person the same coin. So it's a little tricky. What's the question? Doesn't scale very well, right? So there's a bunch of commitments, and you have the same problems Monero, like, you know, your addresses are essentially public-private keys. Now the cool thing is, unlike Monero, you don't have to check each transaction to be like, do I have to decrypt? Is this my public key? Let me decrypt all of the public keys in the chain. But then it doesn't scale super well because effectively you have to check all the commitments. And that just like takes like an incredibly long time. So that's why when you send Zcash, you're like, oh wow, Bitcoin's slow, 10 minutes, half an hour. With Zcash, I don't know, at some point the chain, there was like a spam attack on chain. There was like too many transactions, and checking Zcash transactions took days. Okay, so it's pretty terrible. Like I want to send you money privately, I got to wait a month, a week. This is like kind of crazy, right? So luckily what's happened is that there's various ways to make this less hard. You can do various forms of what's called checkpointing. So you kind of do all these commitments, you kind of compress them. And what this has led to, I don't have a slide on this, but I'll just mention, it's led to a lot of research in zero-knowledge proofs. So part of the problem, you see all these commitments, like this is kind of a mess. Like what if we, improving these commitments and zero-knowledge is a mess, that's like the main slowdown. So they've invented a new hash function for zero-knowledge proofs called the Poseidon hash function, which makes running these commitments, improving them in zero-knowledge much faster than normal hash functions. There's been a lot of work on making zero-knowledge proofs more efficient. The most efficient version is probably bullet proofs, and which are kind of old, and now Halo 2, which is kind of adding bullet proofs to this scheme. And so there's all this research on like simplifying and making more efficient zero-knowledge proofs, and that's it's still slow, but you can. Like, while Zcash itself is the oldest zero-knowledge system and is reasonably slow, I think now, because they cut the chain down and they made it smaller, it's like maybe 30 minutes, an hour to transfer money. But if you want like fast zero-knowledge, it's still kind of like a research problem. But there's a lot of research going on, and so you can have zero-knowledge systems which are pretty quick, where the verification time on the client side is always going to be slow. We still know how to get that to be like more than a few minutes, but the prover side is getting down to like the seconds. So it's a really cool research area. There's tons of papers published constantly on it. But then some people are like, man, that is oh, sorry, I skipped this. But the way you want to think about it is that, sorry, one big question, I just skipped it. One big question is, how do you know you're just not making up Zcash? So you said a bunch of private keys, So a bunch of private coins, a bunch of destinations, a bunch of values. You have a bunch of serial numbers. You have a bunch of commitments. So these commitments are all on chain. And then you can do this kind of mega proof, right? Which proves that all these old coins were valid. All these old coins. The value of the old coins adds up, and you are not printing new coins. So this is kind of like you can imagine, this is not the best graphic, but you can basically imagine you're sending all the old coin transactions in, you can look at all the old commitments and kind of calculate these kind of commitments to serial numbers, and you get a big proof that that there are no fake transactions in the whole chain, and the value of the coins all line up. And you can say, okay, maybe the value of the coins line up with all the secret coins. If you have public coins, remember Zcash, you have public coins mixed with private coins, you can make them all line up. You can say this is the public coin value, this is the private coin line value, and these values all add up to be less than the amount of coins in circulation, or equal to the amount of coins in circulation. And so, yeah, you can do, but people don't really trust it. So I'm going to end on a note, which is some people say, well, geez, this is really a mess. Why don't we just use secure hardware, right? If these people can run run all these commitments and zero knowledge proofs, and they're running these Bitcoin miners, running hash functions, they're buying special computers, why can't they just buy secure enclaves? So we have a bunch of secure enclave people working on making privacy-enhanced cryptocurrency via secure enclaves. And it makes a lot of sense, because then you can just trust the machines. The machines basically keep the values and the transactions private. They can guarantee that the transactions that are ran by the machines, like what you put in the trusted computing base that's hidden effectively, is running correctly. You can get what's called an attestation that's being ran correctly. And so trusted hardware basically prevents computers from accessing keys or accessing members' confidential info, and that this could be a whole alternative and much simpler way, assuming you're running the hardware, of doing cryptocurrency transactions. And there are blockchains in production. The two ones that are most well known is Oasis, also has a token called the Rose token by Don Song of Berkeley, and another, I think it's Israeli token called Secret, SCRT is their name. And so these people basically say, oh, you want to run our system? You have to run trusted hardware, which is, they have, it was originally SGX. Now, there's been a lot of new development, ARM, AMD, Intel has now, I think, TGX. They have new systems now, which are more appropriate for server-side calculations. And so this is still, again, a big open area of research, but there's at least two systems in production that basically say we can accomplish everything Zcash does, but with enclaves and secure hardware. And you're also seeing a lot of usage of secure enclaves and hardware just to not lose the customer's money, right? So I'm using Coinbase. I put my money on Coinbase or Kraken, or I don't know what exchange, Binance. And the danger is, of course, that the company runs away with all your money because you just gave them all your private keys. So when I use a wallet on my phone, the private key is on my phone, and that's great. I lose my phone, I lose my private key. That's terrible. So I should have backup. But when you use an exchange, they're just generating and holding your private keys. And so one question is, can we use secure hardware? There's some also research in MPC and other things, multi-party computation, to basically hold all these customer funds more securely. So there's a whole lot. There's probably even more research and money on how to do this securely than there is on how to do privacy-enhanced transactions securely. So yeah, so I mean, the problem with trying to do everything in software is you end up using a lot of crypto and it's really slow. If you use hardware, you can do things pretty fast and get more or less the same guarantees. And you can also do combinations. So even now there's research on accelerated zero-knowledge hardware. Or maybe we put some of the zero-knowledge system in secure hardware. We keep something on the outside. It's still very much an open field. There's no currently existing design which has consensus that it's the best design in privacy-enhanced transactions. We can all agree it's easy to de-anonymize Bitcoin. We can all agree running a giant blockchain that has everyone's transactions may be a bit nightmarish from a privacy perspective. We can all agree that digital transactions are good. It's easier to do QR codes with your phone than take out money and lose the change, and but there's no consensus in the research or in implementation about how to do privacy correctly. There's some advanced topics we didn't cover. You also can run programs on blockchains where you can verify the input and output. You can even have the program be ran by all the validators. That's called smart contracts. There's even a more advanced research field about how to run smart contracts privately. Maybe you should run them in an enclave. Maybe you can run smart contracts and zero knowledge proofs where you're committing not just to like sending you money, but committing to like a whole program execution, and it all gets incredibly complicated. But it's a huge field, and if you enjoy it, I recommend looking into it. There is still, it's still very interesting. There's a lot of work going on. And AI ends up being a big deal because you can essentially use machine learning algorithms to run these transaction graph analysis and all this other stuff at scale. So de-anonymizing is getting easier every day. It's a great research field for de-anonymization. It's a great research field because all these blockchains give you a giant data set to de-anonymize people, which is usually the hardest thing to get when you're doing machine learning, is to get the data set. So any questions? Go for it. So you will definitely have, unless there's massive political pushback, centrally banked digital cryptocurrencies running in most countries, at least in Europe, pretty soon. Right now, again, we're already deploying what's called wholesale CBDCs. This is for transactions between banks. So I have a bank, I'm using, I forget, ING, and you're using BNB Paribas, and they can settle all their accounts via blockchains. So that already works. But again, that's fine. They can just talk to each other. They use a blockchain. It doesn't have to be public. It's a private blockchain. But they don't really need to use privacy on that blockchain between each other because only they can access it, or the government, them plus the big banks, to make sure that the money isn't like lost and people aren't printing money. I think consumer-facing CBDCs are probably coming. Now, this is much more sensitive in the area where privacy will probably have to happen. Because there's probably going to be massive political pushback. At least the United States is already killing the effort because there should people a little bit uncomfortable with all their, I want to buy a Coke, a Coca-Cola, my Coca-Cola transactions recorded on a blockchain controlled by the government and the bank, and they know exactly, which is close to Visa already, but there's still nervousness about